Welcome to this module, and in this module we will be looking at the full wave rectifier and oscillators. So, another application of operational amplifier. Even we write this basic operational amplifier circuits. Even these basic operational amplifier circuits will get little bit complex as we move on. Alright. So, what we have seen in the last module is the half wave rectifier, right, and I told you the application of the rectifier in the DC power supply, that is right in front of me, right. Yesterday we last lecture or yesterday I do not know when we recorded this particular lecture, we have seen that how a rectifier would work, right, and the idea is that you have the 230 volts AC and you have to convert this AC to DC. Then you need to first use a step down transformer, which is a transformer within this DC power supply, and that step down transformer you have to attach or connect a rectifier circuit, and that will give you the final DC output. So, from AC to DC the rectifier is extremely important circuit. Now, yesterday we have seen a half wave rectifier, that means that if I have a signal, right, if I have a sine wave, only half wave will get rectified, another half will not. But do we need a half wave rectifier? Are we interested in using half wave rectifier or we need a full wave rectification? That means that if I have a signal, it should be completely converted to DC, right. So, that depends on the type of application that we want. Now, what if I want a full wave rectification? What if I require a full wave rectification? In that particular case, I need to design a full wave rectifier, right, and again we keep in mind we will use operational amplifier and use this operational amplifier to rectify the AC signal and get the DC output, So, how we can do this AC to DC, that to full wave rectification, that is the today's module, and we will see. First let us understand quickly what is full wave rectifier, and then we will continue the experiment part. Okay. So, if you come back to the screen, what you will see is we have to understand what are the basic op amp circuits, and today we will understand rectifiers and oscillators. Very important application of operational amplifier circuits. Alright. So, these are the experiment modules, as you can see here, right. We have completed the theory modules. These are experiment modules that we will be using that are used for us to understand how we can apply theory to the experiments. Alright, how we can use our theory knowledge to find out the solution in terms of experiments. So, if you see the first slide, we have the op amp circuits, right, op amp circuits using diodes to act as a full wave rectifier, That means, if I apply a signal, my output would be DC, should be DC. Maybe there are some ripple voltages, that is different case. Okay. There are some ripples and lot of other things are there that we are not considering right now. Our just simple thing is, if I apply a AC, can I get a DC or not? To get the DC signal from AC signal, I need a rectifier, right. Yesterday we have seen that if I apply AC signal to a half wave rectifier, it will rectify half, right. So, we will only have rectification like this. The top was rectified, right, it is gone, only half wave rectification, but here we will be looking at the full wave rectification. So, to understand the full wave rectifier, let us see the circuit which is here in figure 1. Alright. Here we are using two operational amplifiers, 1 and 2, right, and we are using two diodes A and B. Easy, we are using two diodes, we are using a inverting amplifier, right. See, signal is given to the Vi is given to the inverting terminal of the op amp, inverting amplifier, right. and let us see how this circuit operates. Let us see how this circuit operates. All right. So, you can see a full wave rectifier circuit in figure 1, which is this one. For a positive input, that is V I greater than 0, this V I greater than 0. In this particular case, what will happen? What will happen? You see, V I is greater than 0, then my output, right, will be such that my op amp will start, my diode D1 will start conducting, my D1 will start conducting, and D2 will be off, right. D2 will be off, because my inverting input V I is greater than 0, means what is greater than 0? What is non inverting amplifier, non inverting input? Non inverting input here is grounded, right. You can see this is grounded, that means that is 0. So, if my input voltage V I is greater than 0, that means it is greater than the non inverting terminal, then my output would be minus, or it will be 0, right. It can be minus, 0, whatever it is. That means that this will be plus, this will be minus, this will be minus, this will be plus, correct. That means my diode, right, my diode, that is diode D1, right, or diode A will start conducting, and diode B will not conduct, because this is a opposite polarity. To conduct the p-n junction diode, we need to apply positive to anode and negative to cathode, right. So, if I draw a diode, you see this is anode, this line represents cathode. If I want to conduct, that means if I want to operate this diode, then I have to apply positive here and negative or ground here, then only this diode will operate. If I do reverse of this, that means I apply negative here and if I apply positive here and apply negative here, then this diode will not operate. This we all know, correct. So, using this principle of the diode, what we find is that if my V I is greater than 0, we are concentrating only on this particular operation amplifier. Okay. So, if I V I, this one V I is greater than 0, then my diode D1 will conduct, D2 will not conduct, that means D1 is on and D2 is off. So, if I want to draw equivalent circuit in this particular case, then the equivalent circuit is as shown in figure 1a, this one, right, because you see R, this is okay, then we have R2, this is 10 kilo ohm, all right. Then we have this diode conducting, this diode is conducting, right, that means it will have directly conducting, that means connected here. Then we have R, which is another one, and R4, right. Correct, you got it. Again see, super easy. Was that when I apply V I greater than 0, then this diode starts conducting, means I can just draw a line, this will not conduct, so it will block, right. So, now what I have, I cannot see this one, I cannot see this one, right, I can only see the remaining part. When I have remaining circuit, then how it will be, this one would be there, this one would be there, which is here and here, correct. Then I have R3, I have R4, I have R4, I have R3, this is connected here like this is connected from here to here, okay, and then we have A2, So, you see here A1, A2, that is the equivalent circuit in case when V I is greater than 0, right. So, this is what we are saying, the equivalent circuit is as shown in figure 1a, which is this one, when you have Vi greater than 0, where both the op amps A1 and A2 will act as a inverter. Now, you see here, right, here if I apply voltage, let us say 1 volt, my output will be, my gain is 1. So, this will be minus 1. If I apply minus 1, that will go to here, right, my gain is again 1, this will act as 1. So, this will also act as an inverter, this will also act as an inverter. That is why this sentence says that in this particular case, the first case, when I have Vi greater than 0, when I have Vi greater than 0, both the op amps A1 and A2 acts as a inverter. Alright, this is easy. Now, let us see the second case. Let us see the second case. Let us see the second case. What is second case? Second case is when my Vi is less than 0. When my Vi is less than 0, in that case, what will happen? If my Vi is less than 0, then diode D1 is off, right. If my Vi is less than 0, now in this case what will happen? This will be positive, this will be positive compared to this terminal, right, and this will be positive, this is ground, right. So, this D2 will start conducting, D will not conduct, D1 will not conduct, D2 will start conducting, D1 will not conduct. That means that for negative input, Vi is less than 0, Vi is less than 0. In this case, diode D1 is off, and D2 is on, correct. The equivalent circuit is as shown in figure 1b and figure 1c. Let us see equivalent circuit, alright. So, what we have seen, at Vi is less than 0, this will not conduct. So, we cannot consider this, this will conduct. So, we can short this like this, right, is not it. So, now what we have? We have this one. So, let me just write down here like this, right, this is there, this one is there here, R3 are here, R4 here, correct. Now, this resistor here, correct. Why? Because this diode D2 is conducting, right, and D1 is not conducting, So, here you can see the D1 is not conducting. So, we have no circuit or we have no connection in this particular case, which is your figure 1b, right. So, it is very easy to draw the equivalent circuit of the diode of the figure 1, right, when D2 is conducting and D1 is not conducting, right. D1 is not conducting, that means there is nothing here, D2 is conducting, that means there is short here, this is the circuit, figure 1b. Now, what we see in figure 1b is that you have resistor R and resistor R in series, right, that gives you 2R, right. Or if we further work on this particular circuit and you solve it, what we find is that the equivalent circuit of this particular figure 1b will be this one, right. This is the voltage that we have -2/3 1. So, how it comes? So, if I consider this, right, then the voltage at the non inverting terminal will represent -2/3 of Vi, This is the circuit which is equivalent circuit of figure 1b. Now, from this particular figure, what we can see, that after solving figure 1c, my Vo will be nothing but minus Vi, right. If I solve further this figure, right, 1c, what will I obtain? Vo will be equals to minus Vi. This is what we get when we have D2 conducting, D1 not conducting, right. Anyway, so what will happen? So, hence for Vi is less than 0, Vo is positive. For Vi less than 0, your Vo is positive, right, and for Vi greater than 0, we will see what is the Vo, we will see what is the output voltage. So, the point is that when we want to understand the full wave rectifier, the concept is super simple, that when we apply input voltage greater than 0, my diode D1 is conducting, D2 is not conducting, the circuit will be like this. When I apply Vi less than 0, diode D1 is off, D2 is on, I have equivalent circuit like this, which is equivalent circuit to this, and from solving this we have Vo equals to minus Vi, right. Now, let us see the experiment. So, we had to first perform the experiment for the full wave rectifier, and here what we see is, if I want to perform the experiment for full wave rectifier, I have to connect the circuit which is shown in figure 2, So, what we will do is, we will connect this circuit which is shown here. We have to see that we have to apply 5 volts peak to peak at 1 kilohertz. We have to apply here 5 volts 1 kilohertz, right, at here. Observe the output Vo, we have to observe the output here Vo, and we will note down the peak to peak voltage value. We will note down the peak to peak voltage value. The same time we will observe the amplitude of the waveform. We have to also observe the amplitude of the waveform, and then finally, as usual, we will comment on the shape. Comment on the shape of what? Comment on the shape of the output signal, right. So, what we have to do? We have to connect the full wave rectifier, right, in this particular configuration, and we will apply 5 volts peak to peak sine wave, and we will measure the output voltage, and we will also see the waveform. So, to do this particular circuit, right, what we have to do? We have to have 3 different things. One is, for here we need function generator, we need function or frequency generator. Then we need for output voltage, to measure the shape, comment on the shape, we need digital oscilloscope. Okay. So, we need 2 things, one is function generator, one is DSO, and we have to apply biasing voltage. That means, we need what? We need the DC power supply. Now, we will see how we can use a simulation by using multisim tool to see the rectifying action of the signals. At the same time, we will also use the TI board for the experimental part. TA Anil and Sitaram will take the experiment, and will show you the experiment how it can be done. If you have any questions, feel free to ask me in the forum, and I will get back to you.
Now, we will see the working of the full wave rectifier using multisim. So, let me open multisim, right. So, I will keep both side by side, right. So, this is the circuit that I am going to build. For this, I will take 2 op amps. So, one op amp I am taking this, as well as other op amp this one. This is U1, I am rename it as A1 and A2, so that it will be look similar to what we have seen in the circuit, and this as A2, right. Let me flip this. Okay. So, I will take all 5 resistors here. So, in this case we have used 10K resistances, 10K, this is 10K, this is another 10K, this is another one, and this is the other one, other resistor as a at this point. I will take 2 diodes, because since we are realizing a full wave rectifier, it requires 2 diodes. Let me place both the diodes, one diode and other diode here. So, I will make the connections. So, first R1 has to be connected to the negative terminal, and whereas R2 the positive terminal of A1 operational amplifier has to be connected to the ground, right. So, if you remember our circuits, we will generally connect 2 resistance even at positive terminal of an operational amplifier in order to remove the offset currents. Those resistance are the feedback resistance and input resistance. So, in this case I am not connecting it, right. So, let me connect all the let me make all the connections. And the resistance should be of 10K, that is what the complete explanation, the theoretical explanation was carried out by considering the 10K. So, I will replace the 1K resistor with 10K, that means since it is a simulation I will simply change the resistance values 10K, even this one as 10K and 10K, right. So, this negative I will be connecting it here, whereas this to here, right. So, the input will be connected at R1 resistor. So, what I will do is that I will take AC voltage, I am connecting AC voltage here, the peak to peak value I will be making it as 5. So, peak to peak is 5. So, 2.5 is the peak value and the other terminal should be connected to the ground. So, I am connecting it to the ground. So, now the circuit is ready. So, in order to visualize the input and output and to do the comparison, what we have to do is that we have to consider the probes. So, I will take one at the input side, right, other one at the output side. So, if you remember, so when D1 is on, this is how the complete system will be. So, what happens, a diode D1 is on, it acts as an inverter, so that whatever input we have given you will get as an output, that means you will get the positive peak. Whereas, when D1 is off during the when the input is negative peak, when D1 is off D2 will be on and this will be the circuit. So, finally, we will get minus Vi. So, since this is also negative and this is also the negative in the output. So, both together you will get a positive peak, right. So, let us see whether we are getting the same response even here. So, in order to do that I have to go to split, we will see, and let me run. Yes, when we see here, right, the green represents our input, right, whereas the blue represents our output. So, if I see that when you compare with half wave rectifier as well as full wave rectifier, during the half wave rectifier we will see the pulses only whenever there is a positive peak. So, whereas in case of here full wave rectifier, even during the negative cycle the output will be converted into the positive cycle. So, that is the speciality of this circuit. As a result, we will get a pulsating circuit. So, now if you observe here carefully, even in case of the negative peak, we are getting a positive pulse, that is because of here this particular circuit. So, when we realize the complete circuit, the complete when the D2 diode, so that means when you observe carefully, during the positive peak of your input signal, the D1 will be on and D2 will be off, so that it is nothing but your virtual ground. So, as a result we will get a minus of minus. So, this is a minus and this is a minus, whatever we apply the same thing we will get it as an output. Whereas, when the D1 during the negative half cycle, when the input is a negative half cycle, the D1 will be off and D2 will be on. So, as a result when we realize the circuit, it will become minus Vi. So, it is nothing but minus of your input voltage. So, since input voltage is negative, so minus of your input voltage will become the positive. So, the amplitudes will become there will be a change in the phase of your amplitudes. So, that is why you will get a positive peak even when there is a negative signal. As a result, you will get a complete pulsation, right. So, let me change some frequencies. I will start with some 100 Hz. So, we can observe. So, to realize it, what I will do is that I will change this time divisions, even then we can see here, and I will go with the 500, right, same, and 1000, 1 kilo looks similar, then I will go to 5000. Right, we can clearly see that no matter what, any frequency whichever the op amps can be operated in during that frequency, this particular circuit is completely converting it to a full wave rectification. Now we will see the experimental working of the same circuit using TI board. When we look into the TI board, so here we can see the complete construction of whatever the circuit that we have seen in the multisim. So we can see both the diodes here 1 and 2, and we have other resistors. So we have a total of 5 resistance here. So all 5 resistance you can see here connected, and we are using this particular portion of an operational amplifier. So since this is TL082, we are using both op amps in single IC. So one part we are connected to the first portion, and the other part we are connected to the other portion. Now when you look into function generator, so we will be applying input voltage of 1 volt peak to peak and a frequency of 1 kilohertz as an input to this particular operational amplifier. So that means through the circuit, and we will see what is the response using CRO. So let me connect the input to the circuit, right. When we see what is the input connected to the on the CRO. So now here we can see what is the input that we have connected to the circuit. So that input we are generating using a function generator. So the peak to peak voltage is of 1 volt and the frequency is of 1 kilohertz. So now in order to understand how exactly the circuit output is of, we will connect the output of the circuit to CRO. So let me connect it to the output. So this particular pin is the output. So when I look into the CRO, right, here we can see the input is completely sine wave. We are getting the rectified output. So we can see the pulsation. So no matter whatever the input that we have, right, whatever the frequency that we have, we can completely see the positive peak as well as the negative peak will be completely rectified and converted as a positive peak, and the amplitude remains same. Only thing is that the phase will be different. Now when I change the frequencies, let me change the frequencies. So I'll go to frequency. I'm just going to 2 hertz. So here we can see 5 hertz, sorry 3 hertz. Even then it remains same, right. Now it is in 5 hertz, 6 hertz, 5 hertz now. So let me slowly decrease to the lower frequencies too, right. Still the input is of sine wave, but output you can see the pulsation output. So that means whatever the input frequency that I am applying as an input, right, as long as it is a sinusoidal signal, the negative peak, the negative pulse will be converted into a positive pulse. So as a result we will get a pulsation output. Thank you.